I'm going to start by drawing a 3 centimeter straight line using a ruler across my page. So that's 3 centimeters. I'm going to do this fairly carefully. I'm going to do this in the middle of my page so that I've got a good amount of space around the outside. But there is my 3 centimeter line. I'm then going to choose one of the ends of this line. I'm going to pick this left-hand end. And I'm going to, at a right angle, draw a 4 centimeter line. That's coming up from it. I'm going to do it by eye. I'm not going to measure the angle, but I'm going to draw what looks like a perpendicular line. That's at a right angle there. I'm going to mark the lengths of these sides on as well, 3 centimeters and 4 centimeters, just for future reference. I'm going to mark in the right angle as well because we set this up to be a right angle. I mean, okay, probably isn't exactly a right angle because I've done it by eye, but allowing for that, I'm certainly intending for it to be a right angle. It's a sketch anyway, it doesn't really matter too much. Final thing I'm going to do with this drawing before I start doing some actual maths with it is I'm going to join up these two ends of the lines to make a triangle. Now I'm not going to measure the length of that side. What I'm going to do is I'm going to do some maths to calculate it. The idea being that if I resist temptation to measure it, I can measure it at the end and check that it matches the number that I've worked out. What we have here then is a right-angled triangle. We know it's a right-angled triangle because there is a right angle in it. We have a 3 centimeter side, a 4 centimeter side, and another side there. I will tell you that the other side is going to be longer than the two that we've got. The sloped edge of a right-angled triangle is always going to be the longest side that we have. The one that is opposite the right angle, the one that the right angle points towards. The right angle seems to be pointing towards that side there. That is going to be the longest side. So we are expecting that side to be longer than 3 centimeters and longer than 4 centimeters, but probably not too much longer. Here's what I'm going to do to work this side out. First thing I'm going to do is I'm going to draw a square coming off this side here, where this 3 centimeter edge is one of the edges of the square. I'm going to draw the square on. Now, if it's a square, all the sides need to be the same length, so I'm going to draw 3 centimeter lines coming off here and here, and then I'm going to join them up to make a square. So this is a square with sides of 3 centimeters coming off that 3 centimeter edge of the triangle there. What I can do with this square is I can work out the area of the square. The area of this square will be the 3 centimeter edge here times the 3 centimeter edge here is 9 centimeters squared. And the area of this particular square is 9 centimeters squared. I am going to do now the same with this 4 centimeter edge here, and I'm going to draw a square coming off that side. It's a square, so all of the sides have to be the same length, which means they all have to be 4 centimeters in length. So I'm going to draw a 4 centimeter side coming off here, and a 4 centimeter side coming off here. And then I'm going to join them up with another 4 centimeter edge. So that is a 4 centimeter edged square coming off the 4 centimeter side of the triangle. I'm going to work out the area of this square here now. The area of this is going to be 4 times 4. The 4 centimeter times the 4 centimeter is 16 centimeters squared. The final thing I'm going to draw on this diagram is I'm going to draw another square coming off this long edge here. Now I don't know how long this long edge is, so I don't know how big to make my square. So I'm going to do it roughly by eye. I'm going to draw an edge that looks about right for the length of the line that I've got there. Something that looks about right. It doesn't really need to be super exact for this because we are roughing it. It's enough to just give us an idea. So there is another square coming off that edge there. That looks like it could reasonably be a square. Now I don't know how long this is, which means I don't know how long this is. I could measure it, but that's not the point. We're trying to work this out without measuring it. What I can do, it turns out, and there are various ways to prove this, and we'll come back to that shortly. It turns out what I can do is I can take this area, the 9 centimetres squared, and I can take this area, the 16 centimetres squared, and I can add them together. And they will give me, when I add them together, the area of this large square here. Go with me on this one, trust me, and we can come back to proving it in a bit. The area of this large square here is going to be the area of the other two squares added together. The 9 plus the 16 is 25 centimetres squared. And again, we're just taking that on trust for the moment. Now we have the area of that square. I am telling you that the area of that square is 25 centimetres squared. It's the 9 centimetres squared plus the 16 centimetres squared, added together to give us 25 centimetres squared. Problem is, we weren't interested in the area of that square. We were interested in one of these sides. Now think about where that area has come from. If that area had come from a calculation involving the square, what we'd have done is we'd have times this edge by this edge. Now these two edges are the same size, which means we are doing a length times itself to get 25. Timesing something by itself, we could alternatively call that squaring it. We have taken this length here and we have squared it. We've timesed it by itself. We've squared something to get 25. Which means to undo that, we have to say what number did we square to get 25, and we have a symbol for that. We have a process that we can do to undo a square, and the process that we can do to undo a square to answer exactly the question of what did we square to get 25 is we can take the square root of 25, and the square root of 25 says what did we square to get 25, and the answer to that, either because we recognise that 25 is a square number, or we pop that in our calculators, square root of 25 equals, and it comes out as 5. It's a length there, so we would be saying 5 centimetres. And at this point we can measure that edge and see if that is true. And look at that. 5 centimetres. Now the thing is about this process will work for any triangle that has a right angle in it, for any right angled triangle. We can draw a square on this edge, find the area of that square, draw a square on this edge, find the area of that square, add those two areas together, and that will give us the area of a square on this edge. We can then take the square root, and that will give us the length of this missing side. And that's particularly useful when we've got diagrams that aren't drawn to scale. This process, this idea, has a name, and it is named after one of the people who worked with it quite a lot, Pythagoras' theorem, named after a mathematician called Pythagoras. He was an ancient Greek mathematician, and he did a lot of work with this. So it's called Pythagoras' theorem, or often just called Pythagoras. And if we're working with right-angled triangles and we're doing anything to do with the sides, and only the sides, not the angles, of right-angled triangles, then we can do this process. And as I say, it turns out this works for any right-angled triangle. That the area of a square drawn on the long side, that's the one opposite to the right angle, is going to be the same as the two smaller areas of squares drawn on the shorter sides added together, and we can work with them in this kind of way. There are various different ways to prove that this is true, and I would encourage you to seek some of them out yourself. Normally, in an actual lesson, a classroom setting, I would just show you a video of somebody else proving it rather than go to the effort of doing it myself. I'm not going to do that here because I'm not putting somebody else's video in the middle of my own. That's all sorts of legally iffy. But I would encourage you to have a look round on the popular video sharing online platforms and have a look for a proof of Pythagoras for yourself. There are various different ones, some of which involve bits of shape, some of which involve number work. There's lots of different ones. You can find one to suit your particular mood. But this does work every single time with any right-angled triangle. It does have to be a right-angled triangle though. Let's have a look at a couple of examples. Work out the length of the missing edge of the triangle. So we see that we've got a question like this. We've got a right-angled triangle. As soon as we see any right-angled triangle question that's talking purely about sides, we should be thinking, oh, it's this Pythagoras thing, it's this drawing the squares thing. So what we're going to do is we're going to actually draw in the squares. Now this is just a sketch, but drawing the squares in is helpful because you can really track through what you're doing. So I'm going to start with the 8 centimetre side here. And I'm going to draw in a square on this edge. It doesn't need to be particularly accurate, I'm just drawing it in as a guide for myself. I'm going to work out the area of that square. So the area here will be, it's a square, so it's 8 times 8 is 64 centimetres squared. Working in centimetres, so the area units are going to be centimetres squared. I'm going to work out the area on the 12 centimetre side as well. So I'm going to draw a quick square on there. And I'm going to work out the area there. The area there will be 12 by 12 is 144 centimetres squared. Final bit of drawing that I'm going to do, I'm going to sketch myself a square on this edge here. Now the area of this edge is going to be the 144 plus the 64. I'm going to add those two together and that's going to give me the area up here, 144 plus 64. I'm probably going to grab my calculator. Pythagoras questions tend to be calculator based for reasons that we'll see in a minute. I'm going to grab my calculator, 144 plus 64. Comes to 208 centimetres squared. Which is all well and good, but that wasn't exactly what we were looking for. What we were looking for is the length of this edge here. The 208 has come from doing a particular number that we don't know times itself. And when I do a number times itself, I am squaring it. To undo the squaring, I need to take the square root. So my final step in these questions will be this 208. I'm going to square root that. On my calculator, I'm going to do the square root of 208. So I'm going to press my square root button and then 208 equals. On your calculator, it might be the other way around. I'm going to press the S to D button to turn it into a proper decimal answer. And I'm going to notice that this does, in fact, come out as a decimal answer. With Pythagoras questions, it is not unusual that you will get decimal answers for these side lengths. There are a certain number of triangles that do have whole number sides, like the 3, 4 and 5 example that we've just seen. But there are not that many of them. The majority of triangles will have side lengths that have decimals in them. So these questions tend to be calculator questions for exactly that reason. So 14.42225051 on my calculator. I'm probably going to round that a little bit. I don't need to give all of that. I'm probably going to go for something like 1, maybe 2 decimal places. I'm going to write a slightly more full answer first of all, of course, just in case. 14.4222 ... is 14.4 centimetres to 1 decimal place. And that there is my answer to the length of the missing side. It's worth a quick check. There are 2 checks you can do with these answers to make sure it makes sense. It doesn't tell you that it's right, but it tells you that your answer makes sense. The side opposite the right angle, the side that the right angle points towards, like that, is going to be the longest one. So this side that we've been working out here in this example is the longest side. We are therefore expecting the answer to be a little bit more than 8 and 12 centimetres, which it is. 14.4 is the longest of the 3 side lengths that we've got. So that's check number 1. Check number 2, well, it shouldn't be too different from the ones that we've got. 8, 12 and 14.4 seem reasonable. If it had come out as a huge number, that should set some alarm bells ringing with the 8 and the 12. But 8, 12 and 14.4 are close enough for that to seem like a sensible kind of answer. And it is the longest side as we are expecting it to be. Work out the length of the missing edge of the triangle. So, another kind of Pythagoras question. We've got a right angle triangle given to us. We've got some side lengths on it. We're talking about side lengths and only side lengths in right angle triangles. So we're probably thinking about this Pythagoras idea. But there's something different about this question compared to the previous two that we've done. And what's different is that here we are not looking for the length of the longest side. We're given the sloped edge, the one opposite the right angle. And that is going to change slightly the way we do the question. We're given the longest edge, but it's only going to change it slightly. As I'm still going to do the boxes. I'm still going to start by drawing the boxes and working out some areas. And hopefully, by working out what we can work out here, we can see where we'd go with this. I'm going to draw in my 3 squares, my 3 boxes, and I'm going to work out what I can. So in a normal world, this question would go, well, here we go with the 2 smaller areas. So the area of this one here, this orange square, will be 2 by 2 is 4 centimeters squared. So far, so good. And then we'd have the area of this green one. And actually, we don't know what that is. So I'm just going to make a note that it has one. It has an area. And then we'd take that orange area and that green area and we'd add them together to get the purple area up here. Now we don't know what the green one is, but it turns out in this particular one we can work out the purple area. The purple area up here would be, well, 9 by 9 is 81 centimeters squared. And that would have come from, normally, doing, that would have come from the 4 plus the green area to give us the 81 that we then take the square root of to get the 9 centimeters side length. But we're not doing that this time. We don't know what the green area is, but this tells us everything we need to know to be able to work it out. If the 81 should have come from a 4 centimeter squared area added to something else to give us 81, that means that the green area must be 81 less the 4 is 77 centimeters squared. Therefore, the side length must be, well, this 77 came from a number times itself, so the side length must be the 77 square rooted, the square root of 77 to get back to that number that we squared to get the 77. We pop the square root of 77 in our calculators. .774 ... So probably 8.77 centimeters, sticking with this either 1 or 2 decimal places idea. Again, we can do a bit of a check. Is this length that we've worked out the longest edge? Well, no, it isn't actually, and that's good because we're not expecting it to be. The 9 centimeter edge opposite that right angle, where the right angle is pointing to, the 9 centimeters should be longer, and this 8.77 is shorter. Just shorter, but it is shorter. But the 8.77 is also close enough in value to the 9 and the 2 that it seems like a sensible answer. So this is basically the same question as the previous ones, it's just that we're working out a different side. And we've had to do this subtracting here because we're still using the fact that the areas add to the bigger one. The 2 smaller areas will add to give us the bigger one, but we're just having to do a bit of problem solving with that. Broadly speaking, there are 3 types of Pythagoras question. The first is to find a missing side where the longest edge is the missing side. That's the fairly straightforward Pythagoras type question that we looked at with the first 2 examples. The second type of Pythagoras question is to find one of the other missing sides. That's find one of the shorter edges, like the example we've just seen. Both use the Pythagoras process in basically the same way. We just have to manipulate it in the second case for what we need it to do. The third type of Pythagoras question is one of those with a context. You might have something like, here is a wall and the ground, and perhaps there is a ladder leaning against the wall. Given that the wall and the ground will meet at right angles, you might, for example, be told the length of the ladder, and you might be told how far away the ladder is from the wall. And the question might want you to then work out, say, the height that the ladder reaches up the wall. Well, this is nothing more than a Pythagoras question. Given two sides of a triangle, work out the third. So it's just a Pythagoras question, either the first type or the second type, with a bit of context applied to it.